actually a direct TV. There's actually a whole channel. There's nothing but UFOs.
To what?
UFO network.
Oh, we've got an ancient alien. That's
Not
a
the same one.
Spectrum Basic.
Yeah. Ancient alien theory. You have to take to become one of those.
How did they move those rocks?
We don't know.
About the
Aliens
lights,
did it.
we're broadcasting audio right now.
Easter Island rocks. Oh, maybe the Easter Island rocks, because they had to move quite a ways. Pyramid ones. But all the ones that fit together like, clockwork and.
Be
I
around.
don't think I'm gonna worry about it.
No, that's probably the people from Alpha Centauri we got to worry about. They're-
Beetlejuice, they think it's gonna.
It could be the end too. That's the next science fiction book I'm reading. It's a stellar explosion
That's something you
about
brought.
that area.
No.
About 3 light years away. Blast from the. Get there.
I know it's like, okay, well, it's 7 o'clock when we get started. If anyone hasn't signed up, there was a sign-in sheet by the pizza. Appreciate it if you'd sign in, just so we can track how many people are here and record how many IEEE members we have for reporting reasons. Or you can use this QR code and try to register that way. It takes them right, does it take them right to the website or is it? Okay. For those of you who haven't met me before, I'm Chris White. I'm the new chair for the Southern Minnesota section. And I think this is going to be a pretty exciting talk. I'm glad to see some people here that I haven't seen before. So that's nice. For anyone who's online, I'll apologize in advance. I had to get a quick crash course on how to run the streaming, so I hope I do an okay job. But with that, I'd like to introduce tonight's speaker, Dr. Lydia Bardwell-Speltz is a current postdoc fellow at Mayo Clinic under the Department of Radiology under Drs. Xu and Chen. She graduated in 2017 with dual undergraduate degrees in applied mathematics and mechanical engineering from University of Northwestern St. Paul and the University of Minnesota. She completed her doctorate at the Mayo Clinic Graduate School in 2023 under the advisement of Dr. Matthew Bernstein in the Compact 3 Tesla laboratory. Her graduate research focused on MRI safety evaluation for subjects with implanted devices, and she received her certification as a magnetic resonance safety expert in 2022 during her doctoral work. So please welcome Dr. Bardwell-Speltz.
Thank you, Chris. Yes. Let's see. All right. Perfect. So thank you for the introduction. So the title of my talk today is the evaluation of MR electromagnetic fields for subjects with implanted devices. So I'm going to be showing some of the results from one of my projects from my dissertation work. And please feel free to interrupt me at any point. Just stop and address those as needed. So this is just an overview of my presentation. So I'm going to talk about what MRI is, the potential hazards associated with it, and then how we might avoid those hazards. And then most of my time is going to be spent on items 4 through 6, where I'm actually going to talk through one of my research projects. So starting with MR. So magnetic resonance imaging, or MRI, uses a large magnet and radio frequency pulses to create medical images. So MRI has become one of the most utilized medical imaging modalities and is essential for any modern hospital. So all imaging modalities such as CT or X-ray or MRI or ultrasound have different advantages and disadvantages associated to using that modality. So the two biggest advantages associated with MRI are, first, the superior soft tissue contrast compared to other imaging modalities. So I'm going to be focusing on brain scans today. So here I'm showing the difference between a CT image of the brain and an MRI image of the brain. So hopefully here you can appreciate the large improvement in soft tissue contrast in the MRI image compared to the CT image. And then the second advantage of MRI compared to other imaging modalities is there's no ionizing radiation. So this makes MRI extremely attractive for patients who need multiple exams or for children, as there is no concern for ionizing radiations. However, MR is still not considered risk-free. So conducting MR exams can cause significant injury or death to patients or staff if safety guidelines are not followed properly. So there are three main components of an MRI scanner that I'm going to talk about today. The first is the main magnet, which creates the very strong static magnetic field called B0. The second are the gradient coils, and these are used to provide the pulses to spatially encode the MR signal. So there are three gradient coils, GX, GY, and GZ, and gradient pulses usually have a trapezoidal waveform as seen in this figure. So two characteristics that define these pulses are gradient amplitude and slew rate. And slew rate just means how fast a scanner can switch the gradient amplitude. And then the third component is the radio frequency coils, or the RF coils. And RF coils can be split into transmit or receive coils. So transmit coils generate the radio frequency pulse or RF pulse, or called the B1 pulse. And then receive coils detect the MR signal. And then transmit, receive, or TR coils do both. And then additionally, I want to explain the difference between a head TR coil and a body coil, as I'm going to use those terms in later slides. So a body coil is built into the scanner, which we can see here, whereas a TR head coil, which is shown here, is something that's plugged into the scanner to allow for localized RF at the head and neck. So how does MRI work? So our body contains lots of hydrogen atoms, and these are often called protons because the nucleus of a hydrogen atom contains one proton. And protons exhibit a property called spin. This is a quantum mechanics property similar to the angular momentum of a sphere. So typically, these spins exist in random orientations, as shown in this figure. Once placed in a strong static magnetic field, the protons are either going to align in the parallel direction or the anti-parallel direction with respect to that main static field B0. And then a slight majority of the protons are going to exist in the parallel state, which is going to create a net magnetic moment called M0 that's going to be parallel to the B0 field. We then apply a B1 pulse perpendicular to the B0. So this causes the magnetization vector M0 to flip down into the transverse plane. Additionally, once placed in a strong magnetic field, the proton spins are going to precess around the direction of the B1 field, much like a gyroscope is going to precess due to gravity. So when the transverse components of this M0 vector are non-zero, voltage is going to be induced in the receive coils and then recorded as an MR signal. So next, I'm going to discuss MR safety. So many patients undergoing MRI exams have implanted devices, and these devices can be labeled as MR safe, MR unsafe, or MR conditional. So MR safe means the object or device poses no risk to the patient, and that's represented as the screen box here. MR unsafe signifies that the object or device poses a significant risk to the patient, and that's represented as this symbol. And then MR conditional devices are devices that can be safely imaged under specified MR conditions. So that's represented as this yellow triangle right here. So device manufacturers are the one who develop the MR conditions for their specific device. And these are the types of devices that we are interested in for this study. So commonly imposed conditions for the device include a maximum main magnetic field strength, or B0 field, which we talked about, maximum spatial field gradient, DBDZ, which is how fast the B0 field changes along the direction of the scanner, maximum SAR or B1 plus RMS, and I'm going to describe SAR in a little bit more detail later, and then maximum gradient slew rate and the type of RF transmit coil. So typical static field values or B0 values of an MRI scanner are 1.5 Tesla or 3 Tesla, which is really large compared to the Earth's magnetic field, which is 0.05 millitesla. So the MR environment is going to create complications for subjects with implanted devices because most of these devices are made from metal. So there are 4 important electromagnetic fields: the main magnetic field B0, which we've already talked about, the spatial field gradient, the imaging gradients from the gradient coils, and then the B1 field. And then this table shows the amplitude and pulse durations of these 4 different fields. So note that the static B0 field and the spatial field gradient are always on, meaning that these fields are going to pose a hazard for subjects with implanted devices, regardless if the scanner is running or not. So this chart shows the potential sources of hazards for subjects with implanted devices based on those 4 electromagnetic fields. So some of those hazards include translation, torque, device malfunction, or localized heating of the device, which could then burn the subject. So next, I'm going to give some background on a compact 3T scanner. So a compact 3T scanner was developed as an NIH-funded collaboration with Mayo Clinic and GE Research in New York as a technology demonstrator. The compact 3T is not FDA approved, so it is a research-only scanner. The figure shows the size of the compact 3T on the left compared to the size of a whole body system on the right. The compact 3T uses 12 liters of liquid helium compared to 2,000 liters in a whole body system. And this is important because helium is a non-renewable resource that is in short supply. The reduced size of its gradient coils reduces the associated power consumption, acoustic noise, and peripheral nerve stimulation. The reduced size also has a gradient performance advantage over standard whole body MR systems. So the compact 3T has increased gradient performance specifications of up to 80 millitesla per meter and 700 Tesla per meter per second for gradient amplitude and slew rate, respectively, compared to only 50 millitesla per meter and 200 Tesla per meter per second for a standard whole body system. The compact 3T gradient coil has an inner diameter of 42 centimeters, allowing for exams of the head, extremities, and infants. And this covers approximately 45% of all clinical exams performed at Mayo. To date, over 1,000 scans have been performed safely using the compact 3T under IRB-approved protocols, and the results show improved image quality and scanning efficiency. So because of the smaller scanner size of the compact 3T, the patient is only partially inserted into the scanner bore. A major advantage of the compact 3T for patients with implanted devices is the electromagnetic fields drop off rapidly inferior to the head due to that smaller scanner size. Therefore, devices could be safely scanned at their location even if the labeled MR conditions are exceeded at the location of the image anatomy. So, for example, let's say this subject had a spinal cord stimulator located in the lumbar region or at the yellow star location on this figure. We may be able to perform a brain exam of this subject since the electromagnetic fields drop off rapidly between those 2 star locations. This is the only compact 3T in existence. However, this work could be applied to other head-only systems as well as other whole body systems with reduced bore gradient inserts. So next, I'm going to dive into our research question. So again, many patients that need an MRI scan have implanted devices, and these devices can often only be scanned at 1.5 T in order to satisfy manufacturer conditions. 3T MRI is the preferred field strength used to image the brain because of the increased image quality compared to 1.5 T, as seen in these 2 figures. However, 3T scanning is more restrictive for implanted devices because of the higher field strength. Therefore, it's not available for many patients with implanted devices. And this is again because most implanted devices are made from metal, which is going to create problems when introducing them into the MR environment. So for example, a 56-year-old woman with a breast tissue expander received an MR exam, not here at Mayo, which resulted in the migration of the magnetic ports, which we can see in this X-ray. So the research question is, how can we offer 3T brain exams for subjects with implanted devices while still satisfying device conditions? So this brings us to our research project. So we want to compare compact 3T MR exams of at least 12 adult patients with MR conditional implanted devices and abandoned leads to the corresponding exams acquired on a conventional whole body 1.5T scanner. The purpose is to establish that the compact 3T scanner operates at least equivalently to a whole body MR scanner for routine brain imaging for patients with implanted devices. So the hypotheses surrounding this project are: first, device conditions will be satisfied on the compact 3T. And second, the compact 3T will outperform the whole body 1.5T scanner with significant results based on a radiologist evaluation. And then the project deliverable is a device assessment tool, which is what I'm going to talk about next. So the first step in this project was to create a tool that could be used to conveniently display the relevant electromagnetic fields. So here, main magnetic field strength values were measured using a Tesla meter, and then previously reported measurements of B1+, DBDZ, and then the simulated results for gradient slew rate were all integrated to develop a device assessment tool using MATLAB. So inputs to the proposed tool are the device's location in 3 Cartesian coordinates relative to scanning isocenter, as well as the patient's orientation and anatomic region being scanned. And then the output is the spatial extent of the electromagnetic fields at the device location. So this device assessment tool could be used to determine the safety of scanning subjects with implanted devices on the compact 3T. So to demonstrate this tool's use, consider a compact 3T brain exam for a patient implanted with a Medtronic InterStim device, which is a type of bladder stimulator. So here's the patient's CT. Here we can see the IPG, or the implantable pulse generator. And then I'm not sure if you guys can see it, but the leads come down here to the electrodes down over here. So the manufactured labeled conditions for this device, which means conditions at the location of the device, include main magnetic field strength of 1.5T, a gradient slew rate of 200 Tesla per meter per second or less, spatial field gradient of 20 Tesla per meter or less, and then a head TR coil. So this shows the main magnetic field strength values. The specified location of the IPG is shown as a red circle, and then the lead tips or the electrode is shown as the blue circle. So here we can see the main magnetic field strength is less than 1.5T at this device location. So we know this condition can be satisfied. And then this shows normalized contour plots as a percentage for the gradient slew rate calculated for the 3 gradient axes within the scanner dimensions. So here again, the red circle is showing the device IPG. And then here the blue circle is not visible because the Z coordinate was greater than 80 centimeters from isocenter. And then this lowest blue contour line is 120 Tesla per meter per second for slew rate. So based on these plots, we know that we can satisfy the slew rate condition. And then the program also outputs a value for DBDZ, or the spatial field gradient, which was 4 Tesla per meter for the IPG and less than 0.1 Tesla per meter for the lead. So we know that that device condition can be satisfied. So this example demonstrates how the device assessment tool can be used to help ensure the conditions of MR conditional implanted devices could be satisfied at the location of the device, even if they are exceeded at the location of the anatomy being scanned. So here we have our same image as before, and now we can appreciate the reduced electromagnetic fields between those 2 star locations. So here we have the reduced B0, slew rate, and spatial field gradient. So unlike the previous example, which specified a TR head coil, device conditions often list a SAR or B1 plus limit for the radio frequency or for the RF. So SAR stands for the specific absorption rate, and it's the rate of RF energy deposited in tissue. So the spatial dependence of the B1 plus field is straightforward to measure, and the spatial dependence of SAR is not. So therefore, when assessing the MR conditions for compact 3T scanning, we want to know if we can use the B1 plus squared field to independently measure the RF. So in order to compare SAR, the simulated electric field of the compact 3T scanner was compared to a 1.5T and 3T whole body scanner with both a TR head coil and a body coil using a human body model. So from this data, SAR spatial maps were calculated using the following formula, where E is the electric field, and then sigma and rho are the conductivity and density of the tissue respectively. And spatial maps of the tissue conductivity and density were obtained from those same human body models. So this shows the coronal maximum intensity projection of SAR in watts per kilogram across these 5 different coils. So on the left is the compact 3T, and then the next 2 columns are the 3T and 1.5T body coil for a whole body scanner. So here we can see there's an increase in SAR in the chest region compared to the compact 3T. And then the next 2 columns are the 3T and 1.5T TR head coil for a whole body system. And this shows that the TR head coil largely limits SAR to the head and neck region compared to the compact 3T and the body coils. So the magnitude of the B1 plus squared field and SAR fall off rapidly on the compact 3T along the z-axis and are already reduced by an order of magnitude at a location 60 centimeters inferior to the head. So because this figure indicates that SAR falls off similarly to the B1 plus squared field, we know that we can use B1 plus squared independently to assess the RF. So now that the device assessment tool could be used to assess MR conditions, subject recruitment could begin. So I used the clinical device calendar here at Mayo to look for subjects with certain types of devices, such as spinal cord stimulators, bladder stimulators, pain stimulators, or abandoned leads. And then once a potential subject was identified, the device assessment tool was used and the case was reviewed by an MR physicist. And then they determined if it was safe to proceed with obtaining consent. And then the compact 3T exam was performed under an IRB approved protocol. So we had 10 subjects recruited with stimulators and 2 subjects with abandoned leads, which is what I'm going to talk about next. So abandoned leads are from cardiac implantable electronic devices, or CIEDs. Here's an X-ray of a subject with abandoned leads. So here we can see there's 2 of them, and then they kind of coil up here near the heart. So these are leads that have essentially been left behind. So let's say a subject had a pacemaker, which is a type of CIED, but it needed to be removed. Surgeons will often remove the IPG, but leave the leads because of all the scar tissue that has developed around them. A 10-year study performed at Mayo showed that 8.4% of CIED patients who received an MR exam had abandoned leads in place. Guidance from the Heart Rhythm Society is to generally avoid MR exams when abandoned leads are present. However, the clinical practice at Mayo routinely performs these exams at 1.5T. So the primary patient safety concern for subjects with abandoned leads is RF-related lead tip heating. And while studies of MRI of patients with abandoned leads have been reported, they have all been performed at 1.5T. So the advantage of using the compact 3T scanner for these subjects is the rapid fall off of the amplitude of the B1 and electric field inferior to the head, which was observed in earlier slides. So the 1.5T and compact 3T exams were performed, and next I'm going to show a few of those results. So here, this slide shows the T2 fast spin echo images from subject 1. The whole body 1.5T image is shown on the left with a scan time of 3 minutes, 11 seconds, and the compact 3T image is on the right with a scan time of 2 minutes, 24 seconds. So there's an increase in the visual signal to noise ratio and overall image quality on the compact 3T image compared to the 1.5T image. And here's just a zoomed in version of those same slides so you can appreciate that increase in image quality. So this is the sagittal cube T1 images from subject 7. The whole body 1.5T image is shown on the left, and then the compact 3T is on the right. Again, the scan time is decreased on the compact 3T. And the arrows here are pointing out an enhancing meningioma. So the compact 3T image has increased distinctness and improved signal of the associated dural tail extending inferior to the main mass compared to this 1.5T image. And then there is some expected signal dropout in the upper image cervical spine compared to the 1.5T due to coil configurations. And then here are the results for one of the subjects with abandoned leads. So again, the whole body 1.5T image is on the left and the compact 3T is on the right. And here again, the scan time on the compact 3T was reduced. So here in this figure, the dark matter is, or the dark gray is the white matter, and then the lighter gray is the gray matter. So here we can see the white matter extending into the gray matter in these finger-like structures more clearly on the compact 3T image than we can on the 1.5T image. And then these are a 3D time of flight MRA exam without contrast for subject 12, showing the right anterior circulation. So again, the whole body 1.5T image is shown on the left, and then the compact 3T is on the right with a reduced scan time. And here, again, we have better image quality on the compact 3T image compared to 1.5T. So a blinded consensus review was performed by 3 radiologists for all 12 subjects. The clinical 1.5T and compact 3T exams were randomized in left to right placement, and then a 2-sided Wilcoxon signed rank test was used to compare overall image quality. So this is showing the distribution of the consensus radiologist scores, comparing each whole body 1.5T sequence to the corresponding compact 3T sequence. So here we know the compact 3T outperformed the whole body 1.5T scanner with significant results. So then conclusions. So 3T imaging has become the clinical standard for brain imaging, but it is not clinically available for many patients with implanted devices due to MR safety concerns. So this study demonstrates how subjects with implanted devices or abandoned CIED leads can be scanned at 3T while still satisfying the device conditions. And then compared to the 1.5T whole body scanner, substantial improvement in image quality, such as signal to noise ratio or reduced distortion, was seen on the compact 3T due to various factors, including the increased slew rate and then the increased magnetic field strength. And then if the whole body exam required a TR head coil, additional improvements could be seen on the compact 3T due to the benefits offered by a multi-channel brain coil and parallel imaging techniques. So the hypotheses that the device conditions will be satisfied on the compact 3T and the compact 3T will outperform the whole body 1.5T scanner with significant results based on a radiologist evaluations were verified, and then the device assessment tool was successfully created. So next is future directions. So here, we could obviously scan more subjects and compare the resulting images for the 1.5T scanner and the compact 3T. And then additionally, if the compact 3T scanner was made widely available, device companies could update their labeling to include compact 3T scanning. Now, obviously, this is a long process, but it's not unheard of, as we have seen device manufacturers update their labeled conditions to allow 3T scanning for vagus nerve stimulators after our group verified the safety at 3T. And then finally, I just want to make sure that I thank all the people that contributed to this work. So my graduate school advisor, Dr. Bernstein's support and dedication was instrumental to this research. And then additionally, I would like to thank all the members of the Compact 3T Lab, our Mayo collaborators, and our GE collaborators. And then I want to acknowledge our funding sources as well that made this work possible, including Dr. Bernstein's research grant and then the graduate school. And with that, I'd be happy to take any questions.
How much helium the two different leads use? It was in liters, but how often or like over what time period is that consumption? Is it like
That's like to initially get it set up. That's how much helium it would take.
What was the question?
Asking about the helium, the 12 liters versus the 2,000 liters to get the scanner up and running. The largely reduced amount of helium for the compact 3T compared to a whole body system.
I have a personal question here.
Yeah,
I have embedded gold bridge work. Is that an embedded device?
bridge work.
Yes, it's metal. Or are you only talking about pacemakers or manufactured?
That's a good question. So here we were looking at more active implants, but that would technically be considered a implanted device. But there are certain types of metals that they wouldn't worry about quite as much, just because there's no, they're not magnetic at all. So yes, it really depends on kind of where they are, what they do, and then if they can figure out the composition, they can determine the safety through that. It's a good question. Yes.
So help me with this question. The compact uses weaker fields, therefore the patient has to lay longer in the device to get the same quality of scan as a full body scanner?
No, you have that backwards. Yes, yes. So the compact 3T has higher fields. So it's at 3T, right? Compared to the whole body systems was at 1.5T. So the 3T is higher than the 1.5T. And then because of the higher slew rate on the compact 3T, we're able to get the same scans faster. So our acquisition time is shorter and we're able to get better image quality as well. Yeah, yeah.
Last question. Assuming the MRI is dependent on Earth's gravity, I could not do an MRI.
Can you repeat that one more time?
MRI scan is dependent on Earth's gravity?
No.
No. Can I do an MRI in outer space? Is that possible?
Is it dependent on gravity?
I think he's thinking back to when you're showing the
Precess, so
That's just an.
that was an example, right, of,
But up to one question.
yeah,
If I was on a spaceship.
right.
And I try on a spaceship out in deep space, could I still do an MRI?
I think that you could. I think you could create a magnetic field and still do MR.
Probably the first person to answer that question.
Yeah, you are. That's really interesting. But yes, I'm gonna say that I think that you could. Yep, you could create a magnetic field and, yep. you could do it.
Back
Yeah.
on the helium for a second, is
Yeah.
that to cool the magnets or what's the helium?
Yes, yep, that's its
So is
purpose.
that a closed system then? If you use 12 liters and it's just
Yes,
in there and it's not
Yes.
consumed, it's just,
correct. And well, and there are some systems, they do need to be replenished.
okay,
So that also is one of the problems with MR. They are creating more and more systems that have, I think they're called zero boil off, which means the condensated helium gets reabsorbed by the system, so you never have to replenish the helium. But yes, that's its purpose, is to keep it cold enough so that's superconducting.
okay.
Yep, yep.
All right, so not knowing a whole lot about MRIs, I'm just curious. So could a patient with an implanted device wear some sort of like new material donut shield of sorts, like around their body to locally reduce that magnetic field they'd otherwise be exposed to? Or is there like reasons why that couldn't work?
Couldn't work. That is a good question. Could you wear something to shield?
I mean, I know obviously if it's ferric, you'd want to like bolt it to the table, right? Or something like that, but
I don't know if you'd be able to safely reduce the fields enough that's like, oh, this is really ferromagnetic, but we're gonna throw you in the scanner and we're gonna think it's safe as long as we're covering up that area. I would worry about all the other fields, if, like here I was talking about the spatial field gradient. So when you're moving through the scanner, what about all those changing fields
Right.
or different things? Man, I don't see that as a potential source that like research would go down, but
Sure.
interesting. Yeah. Yeah. I don't know. Good question. Yeah. Yes.
About a year ago, they had somebody from Mayo who was doing artificial intelligence image improvements. Has that been used on either the 1.5T or the 3.3 T pictures to try to see if they both get improved?
So that would get more on the reconstruction side, which I am not, this is not the reconstruction side. I'm sure there are, but I don't know what they are. Yeah. Yeah. That's a good question. Yeah. Yes.
All right, one more, I promise.
Yeah, no, you're good.
So does anyone ever terminate abandoned leads to create, you know, a continuous loop instead of having two
Yes.
independent cables?
But what do you mean by?
Well, so
terminate?
because then you have localized heating at
Yes,
either end,
yes.
so then if you.
They'll cap them. They'll
They'll cap
cap them.
Okay.
Yep, yep. But you still run into, which actually, I didn't have time to get into it, but that's what the kind of the second part of my thesis was focusing on was how to predict that heating for device abandoned leads.
Okay.
Yes, and we had found, just to give you a little, I don't know, some of my conclusions from my other studies, we had found that cap leads are going to heat up less than uncapped, which has been seen previously. But yes, that does make a difference in how much heating is going to be absorbed by the patient. Yeah.
Okay, and what
definitely.
exactly is capped mean?
So they'll put like a little plastic cap at the end of the abandoned lead. They've also tried metal, but they learned that that didn't work very well.
Yeah.
But yes, there's been a lot of research kind of surrounding that area. But yes, that the clinical practice is to put a little plastic cap at the end of the abandoned leads to try to protect against heating.
Yeah.
Yep.
Okay.
Yeah, good question. Yeah,
So you mainly show the image comparison between 1.5
Yeah.
and 3T.
Yep.
And you are looking at the whole body and the head. So I'm curious about like what if the implants is around the head,
Mhm.
the image quality is still preserved?
Yes, that's a good question. So here, we didn't do any devices that were in the head because the advantage of using the compact 3T is, like I had said, the fields fall off pretty rapidly. So we were looking for anything below the clavicles. Else it doesn't make sense to scan them on a compact 3T. If we wanted to move this project forward, another potential area could be, say a subject had a device in the brain. We wouldn't want to scan the brain, but maybe we would want to do a ankle scan or a knee scan and then compare that to 1.5T. So then the device is still far enough away from isocenter that we would get the advantage of the stronger fields of the compact 3T and then be able to compare that to 1.5T. But we wouldn't do a brain scan of a subject like that. Yep. Yep. They're all conditioned to 1.5T. Yep. Yep. That's a good question. Yes.
So have you done any work with the compact 3T and MRE scanning, or has it just been MRI scanning?
I haven't personally, but our group has done some, MRE scanning of the compact 3T. Yep. I don't know any of the conclusions there, but yes, there's a group that is actively studying that. Yep.
For your device assessment tool?
Yes.
How long did those simulations take to run?
They take 2 minutes.
Oh,
They're very fast.
very fast.
Very fast. Yep. All the input, like I had said, all you have to input is basically the device Cartesian coordinates, which you can get from looking at a patient CT or X-ray. And then it'll just spit out all those figures. So you can identify, okay, here's the field at that location, compare it to the device manufacturer conditions. All right, can we scan? Can we not scan? Yep,
So
it's pretty
yeah,
fast.
Pretty close to real time.
Yes, yep. And a lot of these patients are flagged ahead of time. So the device calendar, I don't know how it works at other institutions, but at Mayo, it's booked out, weeks in advance. So these MR physicists are reviewing the case like a week before they would actually scan the patient. But it could be done in real time. But because we had those subjects kind of in the queue, we were checking it out before we would even, see the subject. Yep. But it could be done in real time. Yeah.
This is also in regard to your assessment tool.
Yeah.
I was curious, since it's aiding in the decision-making as to whether a patient is eligible,
Mhm.
is there a certain degree of precision that you had to reach with that? And
Yeah.
how long did it take to train your model
There was no training.
or develop it?
Yeah, well, and we just did within 5 centimeters. So looking at if we can accurately identify the device location of the CT or X-ray within 5 centimeters, then we could use the device assessment tool and use those results. But a lot of our patients, or some of the patients, I should say, that we had tried to recruit didn't have a past CT or X-ray. So then we wouldn't recruit them because you couldn't know for sure where the device was located. So there was too much uncertainty there, but we made sure we were within 5 centimeters. Yep, that's a good question. Yes, Evan.
Thanks, Lydia. It was good. So how do you determine let's say that you have like a deep brain stimulation.
Mhm.
And obviously that would be in the brain, but let's
Right.
just say the IPG.
Okay.
Are you using the manufacturer's you know, specs?
Yep.
Or do you use the CT and have some type of like, look at the volume of the size of the device, or if you have all these different devices that are being developed now, how are you gonna determine like how much metal there is, or do you just use the specs, or what does that process look like to put it into your device assessment tool?
That's a good question. And on that side, that's the manufacturer's job. So when a patient gets implanted with a spinal cord stimulator, pain stimulator, deep brain stimulator, they're given like a little MR card. I mean, we can also look it up based on their model number or whatever, but they're given a little MR card. So we know the conditions that have been tested for that specific device and we know what's safe. So those are tested before we would see the patient clinically. Those are tested by manufacturers and developed by manufacturers. Does that answer your question?
Yeah, so then I'm trying to think, if you have that information
Mhm.
and you were going to say like, okay, can we put them in the scanner or not? You run the model and say, okay, if it's this far, it'll be a problem or not. And then do you just measure with a tape measure how far away it could be, or what does that process look like? How do you determine how far away it can be?
How far away what could be?
Let's say that you have an IPG that's, you know, down in the abdomen versus in the chest.
Okay.
How do you determine how far away it can be from the coils in order to do it or not?
By our fields, by our field mapping. Right? Like here, let me pull up like here.
Yeah, so you do this field mapping.
Yep.
And
Yep.
you can see the red circle is
Yep.
the device, right?
Yes.
And that's 0.8 meters away from
Yes.
where
Isocenter.
the head coil is.
Yes.
Right? How do you know where the device is? With a CT scan that you merge with this, or?
No, you can measure on a CT scan.
Okay.
You can pull up. And some of that and that's if the patient, right, has a full CT from like the head, which some don't. And so some of that comes down to the discretion of the MR physicist. They can look at the CT that they have and then determine, okay, how accurately can we predict this? If we're getting close to up here and we can't say for sure where the device is located, we're not going to scan them.
Got it.
So there's a pretty big safety margin in scanning these subjects. Yeah.
There's a team thinking about.
Yes,
this. It's
there
not
is.
like it passed the algorithm, let's go.
No. This is just part of their decision process. They take a lot of other things into consideration before they would recruit a subject. Yep.
Sounds good.
Yep. That's a good question. Yes, Dr. Holmes.
So I'm gonna follow up on that question. You showed a lot of the clinical assessment by the radiologist.
Yep.
Whether or not they liked it better, and that's all great.
Yep.
Did you do any sort of a study, blinded or otherwise, with a physicist who has to make that decision? Is it a risk or not? And did the decision change whether or not they had their tool?
Oh, interesting. No, we did not.
So then, what is your sense? If they didn't have this tool, would they have made the same decision? Like, is it so conservative that your tool is not swaying them to use it or not?
I see. Yeah, interesting. Yeah, no, we use the same protocol that the clinical practice does in determining safety. And then this was just an added feature that our physicists could use to determine compact 3T scanning. But we never looked at determining safety with and without this and seeing if it changed the results. That would be interesting. Yeah. Yep. I hadn't thought of that before. Be a good idea. Yeah, Evan.
So David Holmes brings up a good point.
Huh.
You're probably not going to do a study like that in patients.
Right.
Like, let's hope for the best. Let's see if they agree with it. Hopefully they don't get burned. Hopefully they don't get peripheral nerve
Right.
stimulation. What could you imagine would be like the minimum viable experiment to collect preliminary data to tell you about that?
What do you mean viable experiment?
What type of experiment would you run? Could you, in a water bath, or what would an experiment like that to tell you whether or not, to give you quantifiable results to answer a question like that? What would
Yeah,
that look like?
that's a good question. Well, so you could test all of these different fields. So the American Standard, what is it? American Standard for Testing a Material or something like that, gives guidelines for how to test all of these MR conditions. So say I had a new device, let's just say I had a new device and I wanted to test the MR conditions. They give guidelines on how to test for if the device is going to be affected by the magnetic field, so the B0 field, and what strength is going to cause problems there. The spatial field gradient, heating, they give you guidelines on how to test for heating. Torque, they have lots of different guidelines. So you could follow all of those and create a phantom, put your device in and see what measurements you're going to get from that to determine safety. Because yeah, you're right, you wouldn't throw a patient in to test it. You would do those type of experiments. And that's what the manufacturers do with their devices, is follow those type of standards that exist to test all of these different fields to determine safety.
Do they do their own testing or is there like a independent testing lab?
I think it depends on the company. Yep. Some do their own. Yep. Could that not answer your question, Evan?
Well, I'm trying to think, how do you get at the like
Well, but like
prospective-
Dr. Holmes said, maybe you don't scan, you just are getting data for whether or not the MR physicist would okay the person to be scanned.
Yeah, so prospectively, how do you have, let's say you come up with 100 random conditions
Mhm,
and you explain them all,
mhm.
and then you give all those conditions to the MR physicist, say, would you do it or not?
Okay,
And then you run it through the device assessment tool and just say yes or no.
Yeah.
Come up with a set of guidelines.
yeah,
And then see if they match,
Mhm.
or what would be a good way to test that? Cause I feel like that's a really good question, you know,
yeah,
like looking at all these lines, I mean, it doesn't mean anything to me.
Sure.
Or maybe it does, not
Sure.
sure. How useful is it? What would be a study that you could come up with that would tell us if this is useful or not? Other than the ring is outside the lines, we're good. The ring is inside the lines, not good.
I feel like that's a pretty good study because we're able to see within 5 centimeters the field strength at the device location. So that is telling us whether or not it is safe to scan the subject or not. Because meeting the device conditions means that you can safely scan the patient. Those mean the same thing. You meet the conditions, you can safely scan the patient.
But is it too conservative?
Is this too conservative?
Yeah.
This is just showing the fields. This isn't being conservative about anything. This is the fields as they exist. So you can look at the fields, and if your IPG is below the limit that the manufacturer gives, you know, you can perform the scan safely. If it's not, then it's not.
But if you didn't have the lines. you
Okay.
Didn't have the device.
Yes.
And the physicist is like, yeah, we're fine.
So yes, that's a good question. So if we didn't have this specific device assessment tool, manufacturers give you, for each of their scanners, they give you field maps of their
Okay.
B0 field and their spatial field gradient. And so you could look at those maps and
So
compare
this
this
is the
to that.
type
You
of
could
thing.
compare, yes.
Got it.
Yeah, and these
Makes total
overlap.
sense.
Yeah, okay, yes, yep, yep. So that's required to be given to sites when a company gives when a company purchases a MR scanner. You get those field maps. Yep. And they use them to determine safety for devices. Yep, yep. So do you have a follow-up, Dr. Holmes?
Think that there is a study design you could do in people that would be safe in the fact that you could take one or more MR physicists, have them do the assessment as if it was gonna happen, but not have the person who does the final concurrence of putting in the scanner of whether or not they would do it. So you can separate the accurate decision from the perceived aspects of this. Or you could do A/B testing where they actually make a decision without this and then you introduce it. I think the risk here is that if they don't change their mind at all, then if anything, you've introduced more risk. Because if they use it and they were wrong, if they're
Sure.
overly confident,
Mhm.
then they're liable.
Okay,
So, this is true with any sort of device, interventional, FDA approved kind of product. There's always risk associated. At first you estimate that risk and you do that through this A/B testing. And then you say, okay, now we're willing to take that risk and maybe move it closer so more patients can be cared for. I mean, that, if you want to get into device research or moving products, device products, you have to be prepared to go down those hard questions
Mhm.
of how much more risk are we.
Sure, yeah, that makes sense. That'd be interesting.
Just a follow
Yeah,
up.
yeah.
So the higher the energy like Tesla here, the more heat may be introduced to the different movements based on the implants where it is and the magnetic field energy. So I have a question about like if there's a like assessment tool based on the organ, like I know the CT has that kind of risk assessment based on organ
Mhm.
and how many rays and is receiving. But for the MRI, would there be something like that, like assessment to see like where the organ being received higher energy and then what could be the heat range
Yep.
and the risk related?
Yes, that is a good question. And that does exist. They do have, yep, they have it split up for, I think it's called the CEM 43 or cumulative effective minutes. And so for each organ, it tells you how many minutes it could sustain X amount of SAR. Yeah, and those do change because you're right, some tissue is more friable than other tissue. So they have charts for that you could look that up. Yep, yep, that's a good question. Elena.
Is it just the ends of the leads that you're worried about heating, or is there heating elsewhere that's a concern?
That's what our focus was just the lead at the end, at the electrode or the lead
Is
tip.
that just
Yep.
where like the maximum heating is, so that's the only place that you care about?
Well, because it's all if you remember from my dissertation, it's all calculating, it's a line integral along the lead. So it's just summing all the way till you get to the end. So that's where it's going to be at its maximum. So that, and then that could potentially affect the tissue around that electrode, right? So you would care about what that temperature rise would be at that lead tip.
Okay.
And then, yep. Yes,
Is B0 always considered to be a constant?
yes,
Okay.
yep.
All right.
Yes.
Thank you very much.
Yes, thank you.